Good morning, everyone. I hope all of you are doing fine. Today, we are going to talk about another piece which we saw in last video. We looked at the key semiconductor equations, which are defining the physics in most of the classical devices which we see. So you are welcome to check out that video. So today, we are going to talk about a very important thing in your semiconductor, which is electrostatics. What is the electrostatics of a semiconductor? And the reason is, but why there is an electrostatic is that because you are applying a constant field or constant voltage to your semiconductor. Either we have seen there are two kind of fields which we have applied till now. One was which was looking like this. There was a lateral field where we had the metal contacts. You applied a battery between them, right? So there was a field which we have been looking at as a which is resulting into transport is what is our lateral field, right? This is our lateral field. There's another field which we saw in the MOSFET video. So you can check out the physical structure where we related MOSFET, where there's a metal oxide and semiconductor. And when we apply a potential between these two, right, you are going to see a field which is coming, which is the vertical field, right? So whenever there is a field charge interaction, we know that we are in the realm of electrostatics, which is defining, oh, this is the charge, this will also radiate a field, and how would that influence the field within the semiconductor? Because in the end, I know the field is one of the key quantity which is defining how they are moving, right? So it is very important that I look at the field, how the field is, because that is directly resulting into either charge or charge movement. And then we saw there is a very important equation which we have, or physical principle, which is put in an equation where we know that there is a positive charge which is radiating this field around it, right? This is what you would have seen in class 12 physics, or not yet, then it is okay. But you see that there's a positive charge, it's like radiating this field lines, right? Similar to that, there is a negative charge which is absorbing the field lines, right? So what it means is that there is a, by convention, we see a negative charge which is absorbing, right? Right. So positive charge is giving the light, negative charge is absorbing the light. That is the kind of convention which we look at for the field lines, right? So then when we see this kind of convention, based on that, we saw that, okay, if that is the case, then this charge, whatever is surrounding in whatever space we are considering this charge, this should also relate to the field, how the field is changing, because we see the field is changing in space, right? So that is why we also looked at that the dE by dx, let's say if we are looking at 1D, 1D means one dimensional, only the x. We see that d by dx is proportional to rho. Rho means, now let's look at what is rho. So that is the charge density. And we'll talk about the charge density in another video. What is the different kind of charge we have in semiconductors, right? As of now, this is the total charge at some point, right? Total charge density at some point in the semiconductor, right? And then you see that what is this field is relating to this charge. And we saw that this proportionality constant is what is result into a quantity which is a material quantity, which is your dielectric constant, right? So that was what we saw on the video of the semiconductor key equation. Now we are going to look at beyond it, that okay, this is what we know as your Gauss law, right? Now we also know that, oh, the field is not one is applying. What is they are applying? They are applying V. So how does field change with V? And that is something we understand, that if we are, it's basically like this bottle of water, which we saw, right? This is a table and there's a bottle of water. The bottle of water has bottle. There's no voltage applied or no potential energy gain. When you put the bottle of water like this, right, you see there is a movement of the water from, because you have raised this to a higher potential, right? So when there is a higher potential applied, we see that this is the direction of the water movement, and that is what we also result in the electric field. So that means you can see if your voltage, now if I see this picture, how is your voltage changing? Because we know that electric field is what? It's the rate of change of voltage or potential, the rate of change of your potential, right? So if I'm going from x to this point, x1 to x2, I know my potential is increasing, right? And how is the field happening? What is happening to the field? Field is in the opposite direction. So that is what, if you see your E, if it is proportional to dV by dx, you see dV by dx is positive, right? In this direction, your dV by dx is positive because your x is positive, dx is positive, your dV is positive. But while your electric field is in the opposite direction, and that is why you see there is a negative sign when we relate field to the potential. So that means the direction your potential is increasing, opposite to that is your field lines, right? And this is what is the generic uh, mathematics which we have seen. So based on that, if we put in this equation, so this is, let's say, equation 1, this is equation 2. When we put in 2 into 1, what we get is a picture where you see this becomes minus d power square, right? So, and this is equal to your rho by epsilon, or we can take the minus sign here. That is what is also we know as Poisson equation, right? Which is a key semiconductor equation. If somebody is modeling electrostatics, this is what is the key. How, when I am applying a potential, how my charge is changing within the semiconductor results in a local field or local potential distribution. So that is why when one is studying semiconductor, it is under the field, it is very, very important that one understands how, when I'm applying this external potential, how at every point in my semiconductor, if I were to look at how my charge is at these points, so N and P, which we have looked at, or rho, right? These, then another thing comes, how is my field at each point, right? So Ex, let's call it, all of our are X, right? Because we are considering, let's say, X. And how is my, because of the field at which is different at every point, there is a potential which would be different at every point, right? So that is what are the key quantities when you are trying to understand semiconductor devices, that how at every point what is happening, why the electron injection is lesser, or why electron is not able to travel nicely, or hole is not able to travel. These are the key quantities one would look at, right? This potential is also used for us to plot something called Venn diagram, which gives us a picture of that what is happening to the bends or the floors. Because you see these floors which we talked about, right? Floor 1 on floor 0, we said they are flat, but when you know that there is some kind of earthquake which is your potential is giving, right? This is the earthquake which this potential is giving, then you see it's like earthquake because it is trying to move the system, right? So then if that is the case, you see that this floor will change, right? So this may tilt like this or whatever way it can tilt, right? So these are called the change in the Venn diagram, which is what we plot with these lines. Okay, and we will talk about Venn diagrams when we move to some interesting semiconductor devices. As of now, we are discussing the role of electrostatics. Oh yeah, so the electrostatics tell me how the charge and electric field are relating in the semiconductor. What can I see with this? And that you can see, my friend, that you can find out if you know the condition of your charge in your semiconductor, what you have doped, you can actually find out how my semiconductor electric field voltages, all these are, right? So it is basically similar to, because now I have a very defining equation which gives me the relation between this potential and this charge, right? And this charge is what is the total charge, which we looked at is the whole charge minus electron charge plus whatever are the dopants, because the dopants are becoming positive, which are leaving positive if they are leaving electron, or acceptors are becoming negative. So that is what we would say this is the total charge in the semiconductor, right? If we are talking about a case where these charge, let's say for example, these electrons are there are holes, there are these things, and the total rho is zero in this, and this we will talk in more detail why it is zero and this is neutral, right? Even when we dope it. So that is the another part which we will talk about in doping. So be with me. Now our objective in this is to talk about that what is the implication of this, right? What is the implication? Oh yes, you are saying rho is neutral. Okay, rho is zero. What is the rho zero meaning? So you can see from your Poisson equation that if you put zero, your d by dx comes to be zero, right? And that could give you that E is some constant value, right? But now the question is, what is this constant value? Because you are saying, oh, my semiconductor is neutral. Is there a field existing in my semiconductor, even if it is neutral, right? And that is a very good question to ask, right? That what is neutral and what is quasi-neutral and all these points. But what we see physically, so sometimes mathematics tell you it is constant, but physically what we see in a neutral semiconductor that your E, this is very close to zero, or it is zero, nearly zero, right? So that brings to a point that now if I give you a different configuration of rho, you should be able to know how my potential energy or my V in the semiconductor and the E in the semiconductor are changing. And this is widely used in semiconductors. Whenever we are applying voltages, we are seeing how this is changing this kind of thing within my semiconductor, because we are trying to get a local picture, right? So that is what for today. And I hope that this relates whatever we read in 12th physics in electrostatics to context of our semiconductor devices and what is happening in our semiconductor devices. So happy learning to all of you and keep growing. Thank you.